we shall discuss chromophore in UV spectroscopy and the effect of conjugation on chromophores. The part of the molecule responsible for imparting color is called as chromophore. The functional groups containing multiple bonds capable of absorbing radiations above 200 nanometer due to N to pi star and pi to pi star transitions. A chromophore is a part of a molecule that absorbs light, causing a compound to appear colored. Conjugation, which involves alternating single and double bonds, significantly impacts chromophore behavior. It leads to a shift in the absorption maximum towards longer wavelengths, that is redshift, and an increase in the intensity of absorption. Chromophore is a Greek term. Chromo means color and phos means bearer. It is defined as any isolated covalently bond group that exhibits distinctive electromagnetic radiation absorption in the UV or visible area. The chromophore containing compound is chromogen. The electron is loosely bonded in nitrogen double bond nitrogen. These loosely bound electrons required less energy for electronic transition, and the absorption band occurred in the near UV region. Other example of chromophores includes C double bond with C, C double bond with O, and NO2. A chromophore is an atom or group that contributes to the color of a chemical. Molecules absorb some visible spectrum wavelengths while reflecting others. The wavelength reflected by the molecule is what we experience as color. The energy difference between two distinct chemical orbitals in a chromophore falls within the visible spectrum region. When the chromophore was exposed to the visible spectrum, which activated the electrons from their ground state. As a result, when exposed to light, a chromophore changes conformation. If more than one chromophore is required to impart the color in a compound, then it is known as dependent chromophores. For example, acetone having one ketone group is colorless, while diactyl having two ketone groups is yellow. Different kinds of chromophores. There are two kinds of chromophores. One, the chromophores that have pi contain electrons. They only go through pi to pi star transitions, such as ethylenic group C double bond with C and acetylenic group CC. Chromophores that contain pi as well as n non-bonding electrons. This chromophore has a single pair of electrons. As a result, they are responsible for two types of transitions, namely n to pi star, pi to pi star, such as nitro group, azo group, nitro group NO3, carbonyl group, and nitride group. In UV spectroscopy, a chromophore is a portion of a molecule that absorbs UV or visible light, causing the molecule to exhibit color. It is a part of a molecule which is responsible for its characteristics absorption of light. The color arises when the molecule absorbs certain and transmits or reflects others. Chromophores are molecules in a given material that absorb particular wavelengths of visible light, and in doing so confer color on the material. A chromophore is a section of a molecule that causes us to see color. The chromophore portion of the molecule will have alternating double bonds or conjugated double bonds. For example, beta-carotene, the molecule responsible for the color in carrots, has many double bonds. Common examples include retinol used in the eye to detect light, various food colorings, fabric dyes, azo compounds, pH indicators, lycopene, beta-carotene, and anthocyanin. Anthocyanin. Various factors in chromophore structure go into determining at what wavelength region in the spectrum the chromophore will absorb. It defines chromophores as groups that absorb in the UV visible region and undergo pi to pi star or N to pi star transitions. Examples include carbonyl groups, azo groups, and nitro groups. Axochromes are groups that shift absorption to longer wavelengths by extending conjugation but do not absorb themselves, such as OH and NH2. The characteristic feature of chromophores to absorb light of UV and visible wave spectrum from 200 nanometer to 400 nanometer and from 400 nanometer to 800 nanometer respectively. It can be used to determine their concentration by absorption photometry. The method measures the decrease in light intensity when light passes through a colored solution. The functional chromophore group is concerned with molecular design and synthesis of novel functional organic chromophores and their self-assembly properties. Thus, the ultraviolet absorption maximum of a conjugated molecule is dependent upon the extent of conjugation. As the conjugation increases, the molecular orbital energy decreases so that the pi electron transitions occur in the UV and visible regions of the electromagnetic spectrum. Molecules or parts of molecules that absorb light strongly in the UV regions are called chromophores. Definition. A chromophore is a covalently bonded group within a molecule that absorbs electromagnetic radiation in the UV visible region. Conjugation. Conjugated systems alternating single and double bonds are common in chromophores, and the extent of conjugation influences the wavelength of absorption. Types of chromophores. Examples include C double bond with C, C double bond with O, and NO2 groups. Aromatic rings, multiple double bonds, and other functional groups can also act as chromophores. UV spectroscopy. This technique measures the absorption of UV or visible light by a sample, allowing for the identification of chromophores and their effect on the molecule's color. Axochromes. These are groups that, while not chromophores themselves, can influence the absorption of a chromophore by shifting the absorption band to a longer wavelength. What we call this as bathochromic shift or shorter wavelengths. Hexochromic shift. Applications. UV spectroscopy is used to study the structure and properties of molecules, including the identification of chromophores and their effect on color. The part of a molecule responsible for imparting color are called as chromophores. The functional groups containing multiple bonds capable of absorbing radiations above 200 nanometer due to N to pi star and pi to pi star transitions. For example, NO2, N double bond with O, C double bond with O, C double bond with N, C triple bond with N, and CC have double bonds, C double bond with sulfur, and so on. When a double bonded molecule such as ethane absorbs light, it undergoes a pi to pi star transition. Because pi to pi star energy gaps are narrower, then sigma star gaps that will be larger. Ethane absorbs light at 165 nanometer, a longer wavelength than molecular hydrogen. Axochromes. They are saturated and unsaturated groups that consist of one or more non-bonded electron pairs. This group, which is linked to the chromophore, assists in wavelength variation by raising the intensity of absorption and increasing max. It's a group that does not behave as a chromophore on its own, but when linked to a chromophore, it shifts the absorption towards longer wavelengths while increasing the intensity of absorption. Axochrome enhances a molecule's color, whereas chromophore imparts color to a molecule. So axochromes are color enhancing group. Example of axochromes include OH, NH2, NHR, and NR2. The functional groups attached to a chromophore, which modifies the ability of chromophore to absorb light, altering the wavelength or intensity of absorption. The functional group with non-bonding electrons that does not absorb radiation in near UV region, but when attached to a chromophore alters the wavelength and intensity of absorption. An axochrome is a group of atoms that when attached to a chromophore modifies its ability to absorb light, effectively intensifying or shifting the color of the chromophore. While they don't produce color themselves, axochromes enhance the color of the chromogen by altering its light absorption properties. Axochromes themselves don't absorb UV light but extend the conjugation of the chromophore, leading to a shift in the absorption band towards longer wavelengths, so that is called the redshift or bathochromic shift. They can also increase the intensity of absorption, hyperchromic effect. Difference between chromophore and axochrome. The main difference between chromophore and an axochrome lies in their role in color development. A chromophore is a part of a molecule which is responsible for imparting color by absorbing specific wavelengths of light, whereas an axochrome, on the other hand, is a functional group that modifies the absorption properties of the chromophore. It can enhance the color, typically by shifting the wavelength of absorption or enhancing its intensity. Chromophores are groups that absorb specific wavelengths, while axochromes induce bathochromic shifts. Substituents can cause bathochromic, hypochromic, hyperchromic, and hypochromic shifts in absorption. UV spectroscopy has many applications in qualitative and quantitative analysis. Conclusion. Chromophores, these are the functional groups within a molecule that actually absorb UV light. Common examples include double bond CC, carbonyl group CO, and nitro group NO2. Axochromes, these are groups that, when linked to a chromophore, modify the chromophore's ability to absorb light. They typically have lone pairs of electrons, which can be donated into the pi system of the chromophore, extending the conjugation. Effect on absorption, redshift, bathochromic shift. Axochromes shift the absorption maximum to longer wavelengths towards the radiant of the spectrum. Hyperchromic effect. Axochromes often increase the intensity of the absorption band. Examples of axochromes. Common axochromes include OH, OR, NH2, NHR, NR2, and SH. Now we shall discuss the effect of conjugation on chromophores. Conjugation in chromophores, or the presence of alternating single and double bonds, shifts the absorption of light to longer wavelengths, that is redshift, and increases the intensity of the absorption band. This effect is due to the lowering of energy gap between the highest occupied molecular orbital, HOMO, and the lowest unoccupied molecular orbital, LUMO, as the conjugation extends. In the presence of conjugated double bonds, the electronic energy levels of a chromophore move closer together. As a result, the energy required to produce a transition from an unoccupied electronic energy level to an unoccupied level decreases, and the wavelength of the light absorbed becomes longer. The significance of conjugation on chromophores is a shift in the absorption spectra to longer wavelengths because the gap between the pi bonding and pi star antibonding orbitals decreases. The effect of conjugation. Conjugation, the alternating single and multiple bonds like double or triple bonds in a molecule, significantly affects its electronic properties, including its stability, reactivity, and UV absorption. Specifically, conjugation can lead a decrease in the energy gap between the HOMO and LUMO, resulting in a redshift, longer wavelengths, and decreased absorption in UV spectra. Explanation. Redshift. Conjugation effectively decreases the energy required for an electron to be promoted from HOMO to LUMO. This means the molecule absorbs light with lower energy, which corresponds to longer wavelengths in the visible and infrared region, according to infrared region. Increased intensity. As the conjugated system becomes larger, the absorption, also known as the molar absorbtivity, increases. This means the molecule becomes more effective at absorbing light at the longer wavelengths. Extended conjugation. The effect of conjugation is more pronounced with increasing length of the conjugated system. For example, as the number of conjugated double bonds in a polyene increases, the absorption maximum lambda max shifts further towards the longer wavelengths. Example, beta-carotene. Beta-carotene with its 11 conjugated double bonds absorbs light in the blue region of the visible spectrum and appears orange. Chromophore is the part of the molecule responsible for the color in any compound. This can be any functional group with large number of pi electrons like conjugated double bonds, for example beta-carotene. When a molecule absorbs UV visible radiations, the electrons excites from its HOMO to LUMO. The energy difference between these two levels decides the wavelength of maximum absorption, which is nothing but lambda max. The conjugated double bonds means alternative double and single bonds. For example, beta-carotene contains 11 conjugate double bonds. This conjugated system imparts color to beta-carotene. Other examples are nitro groups and iso groups are very common in coloring dyes. There are 4 types of shift. One is pathochromic shift, which is nothing but red shift, a shift of an absorption maximum towards longer wavelength or lower energy. Hypsochromic shift, which is nothing but blue shift, a shift of an absorbing maximum towards shorter wavelength or higher energy. Hyperchromic shift, an effect that results in an increased absorption intensity. Hypochromic effect, an effect that results in a decreased absorption intensity. Let us discuss the pathochromic shift, which is nothing but red shift. When absorption maximum lambda max of a compound shifts to longer wavelength, it is known as bathochromic shift or red shift. The effect is due to the presence of an axochrome or by the change of solvent. An axochrome group like OH or OCH3 causes absorption of compound at longer wavelength. Pathochromic shifts are also called as red shifts. In essence, the molecule becomes more colored or the color depends as the absorption maximum moves into the visible region of the spectrum. In alkaline medium, p-nitrophenol shows red shift because negatively charged oxygen delocalizes more effectively than the unpaired pair of electrons. If conjugation is increased, the energy gap between bonding and anti-bonding is increased. So it shows that the absorption intensity moves towards the longer wavelength. Hypsochromic shift, which is nothing but blue shift. So it means shorter shifting in the shorter wavelength, towards shorter wavelength. When absorption maxima lambda max of a compound shifts towards the shorter wavelength, it is known as hyperchromic shift or blue shift. The effect is due to presence of a group causes removal of conjugation or by the change of a solvent. Aniline shows blue shift in the acidic medium. It loses conjugation. If conjugation is decreased, the energy gap between bonding and antibonding is decreased. So this picture shows the absorption intensity versus wavelength, and there is the absorption maximum shifts towards the shorter wavelength. Hyperchromic effect. When absorption intensity of a compound is increased, it is known as hyperchromic shift. If axochrome introduces to the compound, the intensity of absorption increases. The intensity of the color increases. The height of the intensity also increases. This shift in an increase of absorption band is called as hyperchromic shift. This means that the molecule absorbs more light at the absorption maximum, leading to a more intense color. So absorption intensity increases. So this shows the increase in absorption intensity. And the last one is hypochromic effect. When an absorption intensity of a compound is decreased, it is known as hypochromic shift. If the intensity of the color decreases, the height of the intensity also decreases. This shift in decrease of absorption band is called as hypochromic shift. So the decrease in absorption intensity is known as hypochromic effect. So put together, this picture shows all the effect of conjugation on chromophores. So absorption versus wavelength. And this absorption intensity, if shifts towards the longer wavelength, what we call this a redshift, and it shows that pathochromic peaks shift towards the longer wavelength. So what we call this is pathochromic. And on the left hand side, we have a blue shift. It means the absorption peak intensity shifts towards the shorter wavelength, hypochromic. And this line refers hyperchromic shift. That means the absorption intensity increases. So absorption intensity of a compound is increased. And this refers hyperchromic shift in which the absorption intensity decreases. So absorption intensity of a compound is decreased.